In this video, we'll be looking at the second half of section 4.2, classifying chemical reactions, which is all about redox reactions. Now, in the first video, we learned about precipitation reactions and acid-base reactions. Okay, so those are the first two types, redox being the third of the major classifications of reactions that we're getting in chapter 4. Now, whereas a precipitation or an acid-base reaction can be balanced by inspection, right, where we add up the total number of atoms on the reactant side and the product side, make sure they're equal to one another by changing the coefficients, we actually can't do that for a redox reaction. Okay, redox reactions cannot be balanced by inspection because we also have to pay attention to the electrons that are flowing around. And so we do what's known as the half reaction method. And that's what section 4.2 is all about. But before we can get to balancing by the half reaction method, we first have to talk about what exactly a redox reaction is. And redox is shorthand for oxidation reduction. And that's a reaction where our reactants are transferring electrons around to make new products. And in this first basic example, right, we see electrons being transferred between the reactant species to yield an ionic product, right? But they can be molecular as well, as we'll see in just a minute. And what the half reaction method shows us, right, is we split the overall reaction, what's on top right here, into individual half reactions where we just track the atoms themselves. So a half reaction for sodium and a half reaction for chlorine. And as we can see, for sodium to go from the elemental solid state, right, to the +1 ion, it has to give up 2 electrons, 1 for each sodium atom. And for chlorine, right, diatomic, to go to chloride, right, it splits in half into 2 Cl-, it has to gain 2 electrons to do that, for our charges to be equal on both sides. And looking at those reactions, we can determine some definitions here. Yep. Notice the sodium atoms lost electrons to gain a positive charge. The chlorine atoms gained electrons to get a negative charge. Okay? So when we have that going on, that's a redox reaction. And oxidation is the term that we have for the loss of electrons. And reduction is the term when we're gaining electrons. So in the previous example, sodium was oxidized and chlorine was reduced. Okay? And we use those terms with respect to reactants. Okay? It's only ever going to be your reactants that are oxidized or reduced, not your products. One thing I'll draw your attention to here, right, is people tend to get a little tripped up with that one. Reduction means you're gaining electrons, right? But reduction and gaining kind of go against one another. The charge is being reduced in reduction, which can only happen by gaining electrons. Okay. And we also have some opposite terms, the agents themselves, excuse me. Okay. So in this case, sodium is being oxidized, but it's also functioning as a reducing agent, also known as a reductant, because it is being oxidized and providing electrons for chlorine to being reduced. So when you see that word agent, it kind of flips the definition. Whatever's being oxidized is also acting as a reducing agent, and whatever's being reduced acts as an oxidizing agent. In that case, this is chlorine because it's removing electrons from sodium. So how do we appropriately use those terms? Individual atoms, okay, are oxidized or reduced, but the entire reactant serves as an oxidizing or a reducing agent. So we'll see what that means in some later examples. Let's look at another example here where we don't have an ionic product, okay? Because we also have redox reactions where we're not fully transferring electrons, right? Rather, we're sharing them because the product in this case is a covalent molecule. So you know it's not a full transfer of electrons to form ions, right? Covalent molecules share electrons in bonds. So in order to relate this to our previous definition, where we see charges going up or charges going down, we need to have the ability to assign oxidation numbers or oxidation states, okay, to elements within compounds, because then we can track how that oxidation number changes, just like a charge. And what this oxidation state is, right, is the charge that the atoms would possess in this theoretical thought exercise were the compound to be ionic. And there are rules for assigning oxidation numbers, right? We don't need to memorize them for everything in the periodic table. There's just 4 basic rules that'll get us there. Okay? And if you understand these 4 rules, you can assign the oxidation number to anything you'll be given in this course. And note that these rules are different from our traditional periodic table rules for assigning charges. Okay. So what's the first rule? If I have an atom in an elemental substance, the oxidation number is 0. So anything that's its most stable state, okay, oxidation number is 0. So iron as a solid, oxidation number of 0. Okay. Hydrogen as a gas, H2 gas, that's its elemental form, oxidation number is 0. Rule number 2, oxidation number of a monatomic ion, so that means a single atom ion, is equal to the ion's charge. So that's easy, right? If I had Na+, for example, the oxidation number is equal to the charge, which is +1. Or if I had Br-, oxidation number is equal to the charge, -1. Calcium 2+, oxidation number is equal to the charge, +2. So those are pretty easy. What's rule 3, right? Make sure you're recording these in your notes. You have to know these rules. How about our nonmetals? Okay, let's see. If I put hydrogen with a nonmetal, then hydrogen always has a +1 oxidation number. Okay. In the rarer situation, if I see hydrogen combined with a metal, then hydrogen's -1. But we're going to see that top one most often. Hydrogen with nonmetals, +1 oxidation number. What about the halogens? Well, if it's fluorine, no matter what, the oxidation number is -1. Okay. For the other halogens in group 17, chlorine, bromine, and iodine, they're usually -1 unless they're bonded to fluorine, because fluorine wins that one out. Fluorine would be -1, and the halogen would be something else. Okay. Or if they're bonded to oxygen. And we have the rule coming for oxygen on the next slide. So your halogens are -1 unless they're bonded to fluorine or oxygen, in which case they'll get a positive oxidation number. Okay. So rule 3 continued, right, is that the oxidation numbers for oxygen, right, is -2, 9 out of 10 times. That's what we're going to see most frequently. Sometimes it can be -1 if you have a peroxide, like hydrogen peroxide, because that's O2 with a -2 charge overall. So each oxygen is -1. Superoxides, which we won't see in this course, O2 with a minus charge, so that has a -0.5 oxidation number. Or if it's bonded to fluorine, then it would have a positive oxidation number. So you see fluorine has no exceptions. Right? Oxygen has very few exceptions, right? And the halogens only have the exceptions if they're bonded to oxygen or fluorine. Right? So that's it in terms of rules. We just have to take number 4 to figure out anything else that would be in a molecule. And rule 4 tells us that the sum of the oxidation numbers for everything in a molecule or a polyatomic ion has to equal the overall charge on the molecule or the ion. So when we add all the oxidation numbers together, if the molecule is neutral, then they should equal 0. If it was a polyatomic ion, then they should equal the charge on the ion. And just one conventional note, typically when we're writing oxidation states or oxidation numbers, we write the sign, then the number, like +2, right, or -3. Versus charge, we typically write the number and then the sign. So you may have seen me writing charges so far as like a 3-. And those are all put together here on slide 57. Hopefully you've been recording these in your notes, but they're all summarized right here. everything together. So let's put these things into practice. 2 examples. Okay. 4.5, we're asked to assign oxidation numbers for H2S. Okay. So I think to myself, what rules do I have to work with? Okay. I don't know anything about sulfur, and that's fine, right? I don't need a rule, but I do have a rule for hydrogen, right? And I think to myself, okay, hydrogen is +1 when bonded to nonmetals. And there are 2 hydrogens in this case. So 2 hydrogens times their +1 charge equals a +2, sorry, I said charge, I should say oxidation state overall. Rule 4 tells me that the sum of the oxidation numbers must equal the charge on the molecule. H2S is neutral, therefore the charge is equal to 0. Oh, made a smiley face there on accident. Okay. So if each of those hydrogens over here is +1 each, that gives me a +2 charge overall. Okay. So for that to be neutral, sulfur must be -2. Right? And that's the oxidation number for sulfur. Hopefully you followed along with that. If not, it's all summarized on slide 59. Let's look at another example here. Now we're looking at sulfite, SO3 2-. All right, again, I don't have a rule for sulfur, so what do I have? I've got a rule for oxygen. This is not a superoxide, it's not a peroxide, and there's no fluorine, so I don't have to worry about any of those exceptions. So for oxygen, it's -2 each, 3 of them. That's going to be a -6 contribution overall. The sum of the oxidation numbers must equal the overall charge in this case, which is -2. Okay. So if I have -6 for my oxygens, right, what must sulfur be? Right. Must be +4. Because it's a -2, -2, -2 for each of the oxygens, -6 total. To make the sum of them equal to -2, right, it has to be +4. And notice that's a different oxidation state from what we just saw. Right? Previous example, sulfur was -2. Here, it's +4. Right? And sulfur can have a variety of oxidation numbers. That's why we don't have a rule for it. Just those basic 4 rules will allow us to determine the other oxidation numbers that we have in this state. Okay. So that can help us with our definition. If you can assign oxidation numbers everywhere, right? A true definition of a redox reaction is where one or more elements undergo a change in oxidation number, right? And that's a good rule for you to have. If an oxidation number is changing in a reaction, it is a redox reaction. Okay? And if something's being oxidized, another thing must be being reduced. Okay? Oxidation means our oxidation number is increasing, going up, right? And a reduction means our oxidation number is decreasing, going down. And there are a couple of types of redox reactions. A combustion reaction is one example. I've alluded to this in the past, right? A combustion reaction where we have a fuel and an oxidant. Okay? Here is the reaction of rocket fuel at the bottom. You can practice assigning oxidation numbers down here, okay, and see what's changing throughout that reaction. Okay? Aluminum and nitrogen are changing in this case. Let's try assigning oxidation numbers to track that. Now, I won't ask you to specifically identify a combustion reaction or our next example, a single displacement reaction. These are both examples of redox reactions, but you should be able to determine them, the fact that they are redox, right? So what will I ask you? precipitation, acid base, or redox. So you should be able to assign oxidation numbers to track that. Okay. Because here's an example of a reaction that might be a little tricky, right? You might see the formation of a solid right here from things that were aqueous and say, oh, that's a precipitation reaction, right? But it's not, because notice it wasn't all aqueous reactants, solid here. Okay. So this is a single displacement reaction, and if you track the redox numbers, they change, or sorry, the oxidation numbers, they change for copper and for silver. And so try that one for practice as well. And you can see that a single displacement reaction is in fact a redox reaction. Okay, so know how to assign and classify these reactions. What we finish this subchapter with, 4.2, as you can see, this is a big one, right, is with how to balance reactions via the half reaction method. Because now that we know what a redox reaction is, remember at the beginning of the video, I said you can't balance redox reactions by inspection, just changing the coefficients. It won't work out. Because redox reactions are typically taking place in aqueous media. Okay? And remember, aqueous means it's in water. So water and hydronium and hydroxide can all participate in the reaction as reactants or products. And while they themselves are not getting oxidized or reduced, they can help with the chemical change in other ways, like transferring electrons or being counterions, okay? Or adding oxygen to form oxyanions, for example. Okay? So they're damn near impossible to balance by inspection. So what do? Right? We balance it by the half reaction method, which we already saw a little example of with sodium and chlorine. Right? We split it into two half reactions and learn rules for balancing those. Okay. This is, in my opinion, for students, the hardest part of chapter 4. You have to have the rules for assigning oxidation numbers, but also have the rules for balancing half reaction methods, of which there are 9 total. And you have to know these steps. What are they? Right? This is best seen by practice. So I'm going to have a separate video where we walk through a reaction and put each of these slides, or sorry, each of these rules into play. But here they are listed in the slides on 70 to 72. What do? You split the reaction into 2 individual half reactions, one for whatever is getting oxidized and another for whatever is getting reduced. Then you ignore everything else that's in the reaction. You just balance whatever element is getting oxidized or reduced. So sodium, for example, or chromium, or anything that's not oxygen or hydrogen. You just balance that, make sure that's equal on both sides. That can be done by inspection, by changing coefficients. But after that, you'll typically run into problems where oxygen and hydrogen aren't balanced. So what do I do to fix that? I remedy the oxygen problem by adding H2O to whatever side needs more oxygen. However many oxygens I need, that's how many H2Os I add. And I have to do that first, right? The order of these steps have to go in order. Because after I add H2O, chances are my H isn't going to balance on each side, my hydrogen. So I fix that by adding H plus to whichever side needs more hydrogen. Okay. And then I look at the charge on both sides. Chances are that's not going to be equal. So I fix that by adding electrons. Okay. Electrons have a -1 charge, so you're always going to be bringing the charge down on one side to equal the other side. Doesn't matter what the charge is, right? It could be -2 on both sides, it could be +4 on both sides, but you have to add electrons to one side to bring the charge down. Then, right, as we continue here, right, we've successfully balanced each half reaction. The first 5 steps you do to both half reactions. After you do that, right, then you have to make sure the electrons that are involved in each of the half reactions are equal to one another. So if necessary, and most times it will be, you multiply each half reaction, the entire reaction, so every single coefficient gets multiplied by the same number, and whatever that number is, it's what's necessary to make sure you have an equal number of electrons in each of your half reactions. And that's the whole goal of the half reaction method, to make sure it's an equal number of electrons, and one of the half reactions is going to have them on the reactant side. The other half reaction is going to have them on the product side. Okay. Then rule 7 is you put your half reactions back together. All of the reactants on one side, all of the products on one side. And then we simplify it by getting rid of things that appear on both the reactants and the product side, which you're always going to have at least the electrons. The whole goal is to have the electrons be the same on the reactants and the product side, so that we cross them out and they don't appear in the overall reaction. And then you check for things like H2O and H+, and see if those can be simplified. Then we finish with rules 8 and 9. Okay. Rules 8 is only necessary if you are asked to balance something in a basic media. Okay. So if you are told you're balancing a redox reaction in an acidic solution, then you ignore rule 8 altogether. Okay. But if you're asked to balance something in a basic solution, okay, rules 1 through 7 are the same. Get your overall balanced reaction. Okay. But then, right, remember from the previous video, H+ comes from acids. So we can't have any extra H+ in our final answer if it's in a basic solution. So we add enough OHs on both sides of the reaction to equal out our H+. Then those H+ and OHs come together to form H2O, and then we'll have some extra OH- on one of the sides, whichever one didn't have the H+. Okay. Then if you've made any extra waters, you simplify that again. And rule 9 is just a check, right? This is a difficult concept, but the beauty of it is that you can always be confident that you have the final answer, because after you do everything, you go back and you check your number of atoms on each side, and they should be equal after the half reaction method. And you check your charge on each side, and it should be equal, right, using the half reaction method. The charge doesn't have to be 0, doesn't have to be neutral overall. It can be anything. It just has to be equal on the reactants and the product side. And if the charge and the number and the type of atoms are equal on both the reactants and the product side, then you can be 100% confident that you're done. That you successfully employed the half reaction method. So the next 8 slides talk us through balancing this reaction, right? Taking Cr2O7 and Fe2+, right, and using the half reaction to balance it. These are nice because it breaks it down step by step, exactly what's being done in every step for both the half reactions, for step 1 through 5. Okay. Then we combine the reactions together, simplify, check our answer, and we get the final answer. So that's 8 slides there, slide 73 through 80 on my slides. I strongly recommend you look through that. Right? I have another example that I'll be uploading to Blackboard to show you how to balance with the half reaction method, but that's something that's definitely going to be on the test. Okay, so practice assigning oxidation numbers, practice balancing by the half reaction method. It is a difficult concept. It's a giant idea from chapter 4, and something that you need to have and be comfortable with before you sit down for the second exam. Okay, so big ideas from here. What is redox? Classifying a redox reaction, assigning oxidation states, and balancing by the half reaction method.